Okie dokie. So the slides we had yesterday. We had this relationship that the right from the beginning, that the different distances we get in a crystal, these d's would be 2 pi over the length of our reciprocal lattice vectors. And we did a whole bunch of stuff. And our final, well, sort of one of the final results would be that what we did quantum mechanically with this so-called Fermi's golden rule, which was how quickly our quantum system goes from one state to another. Okay. It's just vectors, particularly vectors. If we have d equal to 2 pi upon g, then we have agreement. So if we take this equation, 2d sine theta, so Bragg's equation, and plug in for d 2 pi upon one of our lattice vectors, then we'd have something we could work with. And if we rearranged it for sine theta, we would be able to predict the different angles that we would expect to see scattering. So we could have essentially sine theta equals n lambda 2d sine theta. Right. So if I go to the module content page, somewhere down near the bottom, I've uploaded the last 3 condensed matter exam papers. So what we'll do is we'll look through one of the questions on that. So I think from the 1920 paper, there's a question there. An XRD experiment done, gives this diffraction condition as that. Now this is more or less that expression that I just gave a second ago. Where's me? Slide down a little bit this. So verbally, sine squared theta is going to be equal to lambda squared the length of g squared. It's going to be a 4 pi squared on the bottom, something like that. Now, when we had our cubic systems yesterday, we looked at as examples, we had, say, cesium chloride that had real space lattice vectors A along the 3 different directions. And then we had typical lattice vectors are ones that dot with these vectors, 2 pi dot and 0 otherwise. We've got a D vector that's, I think I've got to get to write stuff down, otherwise I'm gonna. So from the previous expression I showed and this expression for a G vector of the cubic crystal, if we put them together, we should get that expression that appears on the old exam paper there. Just get the gubbins out. You can try and get a little bit ahead of me. Right, so we're looking so all of this is, I'm going to say now, is for cubic crystal. This process, this fitting process, gets quite a lot harder for a non-cubic crystal, so we're just going to do it for a cubic crystal. And then we've got our real space vector is formed from n1 a1 plus n2 a2 plus n2 a3, and our vectors are a0 0 0 a0. Do ask questions when I speak nonsense. And we had our reciprocal lattice vector, which we're going to need to get our angles, is going to be h lots of the first reciprocal lattice vector, and b1 is going to be 2 pi upon a. So if I dot b1 with a1, I will get 2 pi. They're both in the same direction. A has got component A and B1, so A1's got component A, its lattice constant, and this B1 is 2 pi upon A. So when I dot them together, so we defined our G vectors to be the ones that would give 2 pi when we dot them together. So I did give a formula with a sort of cross product and a triple product and stuff that was a recipe, but for cubic ones you can just kind of see what they should be. Do it by inspection if you want. And B2 is going to be the same. It's going to be 0, 2 pi upon A, 0, B3, 0, 0, 2 pi. And so that satisfies that if I dot the ith real space vector with the jth reciprocal lattice vector, I get 2 pi this Kronecker delta. That's 0 if I and j are not the same, and 1 if I and j are the same. So if I do it with A1 and B1, I do get 2 pi. These other two components, zeros, like A times 2 pi, and so on for the other. It does satisfy that criteria. So my general G vector here is going to be H lots of B1 plus K lots of B2 plus L lots of B3. So G squared, the square of the length of that thing, is going to be G dotted with itself. It's all, everything's at 90 degrees. So I'm going to get 4 pi on A squared H squared plus K squared plus L squared. That's the length, well, the squared length of G. So when I dot G with itself, I get H squared lots of square length of B1, and the length of B1 is this 2 pi upon A, so I get 4 pi. Yep. So they're integers, sorry. Yeah, this is very important. So where H, A, L are in integers. So that's my reciprocal lattice. So the real space lattice vector, the real space lattice is integer numbers of the real space vectors. So it's the grid you get from the ends of the real space lattice vectors. So put a dot where the end of every one of the arrows is, and the reciprocal lattice is the same thing, but with the reciprocal lattice.
So the H and L, they're like factors, scalar number factors.
Yes, they're just integer numbers. So that means I've taken one of them, two of them, three of them. So that's that lattice point, that lattice point, that lattice point. I've then gone up one, get that one. So this is H is 1, K is 1 as well. H is 2, K is 0. It's they're defining this lattice. So relationship that I had. The other relationship there I had is that, so Bragg's law 2d sine theta equals lambda. We'll just take any one for now. And that d is going to be 2 pi on the length of our vectors. Then it follows that sine theta equals some advanced maths here. Lambda upon 2d equals lambda g upon 2 pi, 4 pi, there's a 2 there. That implies that sine squared theta is equal to lambda squared g squared over 4 pi squared. Something like that anyway. Now, our expression from up here gives us the length of g. So substituting, now I get that sine squared theta is lambda squared 4 pi squared there, 4 pi squared over a squared divided by 4 pi squared h bar, so h squared plus k squared, so squared. Yeah. No. 2 pi squared there. There we go. Final result. 4 cubic. I'll go back if you want. That's the formula. Bragg's law and substituting the length of a reciprocal lattice vector for a cubic crystal. Now, if we look at the things that we've got here, which one am I on? So sine squared, so these are things we measure. We scan our X-ray device over there and we measure what angles theta the thingy comes to life and makes lots of measurements. So lambda is part of the measurement. So we're shining some X-rays of some wavelength at it. So we assume that we know what wavelength X-rays we're shining at the thing. So that's known. A, we want to determine. And these have got to be integers. So if we have h, k and l are integers, if we square them and add them up, we must have an integer. Let's go back. Really? Reaction? So back to the question in the paper. What was measured? It's 2 theta values, these values. So the thing was scanned, the X-rays come in, they reflect off, and then there's a detector over the other side. So as the detector and the source move, they move through angles. So what's being measured is the angles at which there was a sharp increase in X-ray reflection. And these are values that were measured. So I'm going to there. Keep changing key structures. Easiest. So we've got a series of angles at which we get reflections. So the theta values would be those. So we can work out sine theta. The different values of sine theta. So can't zoom in on Excel. I've converted this angle in degrees into radians and then taken the sine of it. Why am I doing this? And then let's have sine squared theta equals that squared. So what I have done is I've taken a series of measurements of theta. I've worked out sine squared theta from them, and each of those sine squared theta values should have lambda squared. So if we're using the same x-rays for each measurement, lambda squared should be the same for each measurement. And if our sample is the same, a squared should be the same for each one of those reflections. 4 is the number 4. Hopefully that will be the same for each of the reflections. Otherwise, physics is going to get quite struggle. So that bit out the front should be the same for all reflections. So this is the last trick. So if I take the ratio of 2 of these reflections, all of this gubbins out the front should cancel out because it's the same for each of the reflections. And I should be left with the ratio of the h squared, k squared, l squared values for the 2 different reflections. So the reflections occur when it's one of these reciprocal lattice vectors, and the reciprocal lattice vectors are defined by the set of integer h, k, and l. So h, k, and l could be 1, 0, 0, 0, 1, 0, which would all have the same length. It could be 1, 1, 0, it could be 1, 1, 1, 2, 0, 0, etc. So whatever we do, we should get our ratio. So if we take the ratio of sine squared theta for 2 reflections, we should get, say, h1 squared plus k1 squared plus l1 squared, where these are the values of these integers for the first reflection. Well, let's do the second one. So if we do the second value divided by the first one, so I'm always going to divide by this first angle. So if I have that divided by that. Oh no. So I've divided sine squared theta for the second reflection by sine squared theta of the first reflection. And I'm not very pleased with the result I get. So, I think these measurements are rubbish. It's not best at all. Yeah. So the only way for this to make sense is if this is a poor measure. Oh, Excel. So this ratio must be, if we've done it right, the ratio of 2 integers. So the only thing that would make sense is that this is 4/3, and it's a bad measurement. Then this was 1. Yep. It's a very bad example here. Okay. So final steps. For these selection rules. So we had for primitive cubic structure, which is the one I should have started with. I'm trying to excavate it. All of the reflections are allowed. So we should have that the first reflection is 1, where h plus k squared plus l squared is 1. And the second line is h squared plus k squared plus l squared is 2. So the first ratio would be 2, 3, 4, 5, and 6. There's another pattern when you've got this BCC, and then odd and even reflections. Odd reflections weren't allowed because there's an out of phase interference effect, so that we will only expect 2, 4, 6. So the first reflection when h plus k plus l squared summed up to 1 wouldn't be allowed. So we'd have first reflection that's observed would be with h plus k squared, h squared plus k squared plus l squared is equal to 2, and then the next one would be 4. So we'd get 2, 4, 6, 8, and so on. And the final one is so-called FCC lattice, face-centered cubic lattice, where the reflections cancel out unless h, k, and l are all odd or all even. So there's only 3 types of primitive of cubic lattice with reflections, and they're only allowed reflections there. If it's primitive, any set of integers allowed. If it's body-centered cubic, there's only all even values are allowed, or face-centered cubic, all odd or all even. And coming back to this data I've just had a look at, this must be a face-centered cubic, which means that all odd or all even. So the first allowed reflection is with h, k, l. Given by 1, 1, 1. So they're all odd. So h squared plus k squared plus l squared. So for this one is 3. So for the first reflection, h squared plus k squared plus l squared is 3. The next allowed reflection with all odd or all even, and I've had a long argument with my daughter about this, but we're saying 0 is an even number for this purposes. H squared plus don't know why I haven't determined. Right, and that's 4. So if I do the ratio of this one to this one, I should get the ratio of the h squared plus k squared plus l squared values for the 2 lines. So I should get 4 divided by 3, and that 1.26 is ballpark 1.3. You wouldn't have to change. You wouldn't have to change this by much. Just for argument's sake, I'll just sort of do a tiny bit of an angling there. It wouldn't take very much to get that to be closer. That's kind of what I'm getting at. Then the next line, the next smallest value of all odd or all even is this. So that is 8, I think. And 8 divided by 3 is 2.2 2/3, which is that. As far as this fitting process is concerned, pretty much, because both the primitive and the BCC should give you that the first allowed line is either a primitive one, it's 1, and then each of the other integers, so it's an integer divided by 1, so you should get an integer. And for BCC, the first one is 2, so it's got to be all even, but then the next one's all even as well. So that for both of those, you should always get integers, and for an FCC, you should always get something that's a number of thirds, because it should be a 3 for the first one. So what this tells us is that this is an FCC crystal. Because measurements might be, but these are the values. And so by doing this, we can work out what the h squared plus k squared plus l squared value is. And then if we go back to our formula, that right to the very so that sine squared theta is lambda squared over 4a squared h plus k. So we've just worked out for any given value, so say for the top one, that 2 theta is we've got the sine squared theta value. We've just worked out what h squared plus k squared plus l squared should be. We know lambda, we know 4, so we can work out what a should be by plugging back in for that line. And we should get the same value for each one. So if I take my spreadsheet, we need to find out the... Okay, and it tells us in the question that lambda is 0.154 nanometers, which you can see is 1.5 angstroms, which is of the order of a lattice spacing. So if lambda equals 0.154 nanometers, so what I should get is 0.15 squared divided by sine squared theta divided by 4, that should be equal to a squared. And then a should be equal to that. I forgot to that times that. Oh, really? Right. Finally. Okay. When I do it for the different lines, I'm getting something that's similar for the different lines. So I'm getting value for the lattice constant that comes out similar for the different. So I'm getting a lattice constant. So the data is consistent with an FCC crystal structure with a lattice constant of 0.65 nanometers. Oh. Right,